Okay, so the objective for the second experiment is to demonstrate how the HPLC works. Okay, uh, how does the separation happen and what it can do in terms of analysis. So I think you have learned this in theory class with Miss Yasmin. So you know what is the concept of chromatography. So basically chromatography is to separate a mixture of compound. Okay, basically, so let's say you have two compound mixed together. So what chromatography can do, it can helps to separate this. And there are various type of chromatography methods. Okay, from the simplest one, like using paper chromatography, and then you have also TLC, thin layer chromatography, column chromatography, and then up to the more sophisticated version like HPLC, UPLC, ultra high performance liquid chromatography, and also gas chromatography. The concept are all the same, as their purpose is to separate the analyte, okay, that you want to analyze. But the advantage of using, for example, HPLC and GC, you can further quantify in terms of, for example, concentration of the sample itself. Okay, unlike other types of the simpler method like paper chromatography or TLC, you are restricted. Maybe for TLC, you can calculate the RF value, how far the spots goes up the TLC plate. But in terms of concentration, it is quite limited. Okay, so HPLC is, I would say, a very complex instrument. Okay, complex machine. It is consists of several components which are combined together into becoming one system. Okay, it doesn't work just by itself. There are parts, okay, which is crucial for HPLC to be working. Okay, if you go and see any type of HPLC, okay, no matter what brand, these 7 components will be available, okay, regardless of any brand. The one that we have in KPJUC lab, if you've been to the pharmaceutical analysis lab, the brand is from Shimadzu, okay, Japanese company. Okay, so among the how to say essential parts for HPLC, you must have the solvent reservoir. So this is where you are going to keep the mobile phase. Okay, so mobile phase is the solvent needed to push your sample through the system and the column, okay, so that the sample or the analyte can move throughout the column. Okay, so you need a mobile phase. And then the pump itself, so this pump is very important. So without the pump, if the pump is not working, then there will be no pressure. So if you inject the sample, then the sample won't be able to pass through the column and won't get analyzed at all. So the pump's function is to maintain the flow rate of mobile phase. And then the third one will be the sample injector. So to inject the sample into a mobile phase, so the sample injector looks like a syringe, okay, but the needle size depends on brand as well, and also the amount of sample that you are injecting. Normally, the volume of sample that you will inject into the system, okay, the HPLC system, is 20 microliter or about 10 microliter. So it is between that. And then we have this guard column to saturate the mobile phase with silica and also to guard the analytical column from impurities and particles. So the fifth parts would be the analytical column. So the analytical column looks like uh, quite a long, maybe there are different length. You have 250 mm, 150 mm, 10 mm, 5 mm metal tube, okay, which contain silica inside it, okay, and the silica particles depends on the type, okay, type in terms of the material, and also they also have different size. All of this information will normally be displayed on the column itself, okay. The most common are like carbon 18, C18 or C8. That means on the silica itself there are um, 18 carbon chain length, okay, which is attached itself to the silica. So it makes the column very non-polar compared to a C8 column. C8 meaning there are 8 carbon chain length, okay, which is attached itself to the silica. And then number 6 is the detector, okay, to analyze the components and separate from the columns. So normally the detector, the most common one is UV spectrophotometer, which is attached together into the HPLC itself. So you don't need to separate and then collect that sample and put it into UVV spectrophotometer using a cuvette. So no need to do that. It straight away run through the UV itself. So there is a built-in UVV spectrophotometer. So you just have to set the wavelength that you want to measure the absorbance. And then number 7 is the readout. Okay, how the data that is has been collected to be presented, or in this case also to plot the chromatogram. So that would correspond to the nowadays it is a computer, a PC with the software as well. Okay, even if you have a PC without the correct software, so you cannot actually have the data out. So the HPLC, as you know, it can work in 2 modes. Okay, one is the normal phase or reverse phase. So in normal phase, the stationary phase is polar. So stationary is the column, the analytical column. So if the analytical column is polar, that means your mobile phase has to be non-polar. While for reverse phase, the stationary phase is non-polar and mobile phase is polar. Okay? And most commonly used is reverse phase, okay, because you can actually know whether the HPLC system is running normal phase or reverse phase just by looking at the solvent use. Okay, if the mobile phase use is using, for example, uh, methanol, acetonitrile, so that would be polar solvent. So polar solvent, polar mobile phase, hence reverse phase. If the system is running normal phase, then for example, the solvent that you have to use is like benzene. Okay, so benzene is non-polar solvent. That means the column that you want to use for that analysis also must be polar. Okay, so there is no column that you can use for both. Okay, so for each phase, there is a specific column. So in this experiment, okay, the sample itself, the purpose is to actually see the caffeine content. So this experiment is designed to introduce the basic use of HPLC for performing a separation and quantitative determination. So what we are trying to do is to actually see the content of caffeine in daily beverages. Okay, like last week I said on coffee drinks, in tea, in carbonated drinks like Pepsi, Coca-Cola, and also you can also check for caffeine in green tea, and also energy drink, okay, like Red Bull, for example. So on to the procedure part, okay. So on to the procedure part. Before you can actually do the analysis, okay, first you must know your sample. That means in this case, your sample or the analyte that you want to quantify or you want to detect is caffeine. Okay, so caffeine. So from this analyte or the sample of interest, the caffeine itself, you can search for the suitable HPLC system. So when I say the suitable HPLC system is the column that you want to use, the flow rate, what else, the mobile phase. If you still remember last semester in the pharmaceutical analysis 1, we have learned the topic of method development. Okay, so how are you going to design the method for this particular analysis, for example for HPLC, and your analyte is caffeine, you can actually refer to pharmacopoeia, in which what type of mobile phase that you have to use, what is the most suitable column, okay, the temperature of the column, and also most importantly the wavelength that you have to set so that it can scan in the UV, giving out proper absorbance, because the wavelength has to be the lambda max. Okay, it has to be the lambda max of the compound, and all of that information can be obtained from pharmacopoeia. Okay, and the procedure that I have here is also referring to pharmacopoeia. So the first step is to prepare the mobile phase, okay, which is the solvent needed for the whole HPLC system. So the mobile phase that you can use would be methanol with water, a mixture of methanol and water. Some references may use ethanol as well, ethanol and water. And the ratio is 80-20, meaning 80 ethanol, 20 water, or up to 60-40. That means 60 methanol or 40 water. And I don't put 80-20 or 60-40. I use the word to. That means you can actually change accordingly so that it suits the HPLC system. Okay, because sometimes it doesn't follow exactly the same. Sometimes you have to change slightly, maybe to 75 methanol and 25 water. So this is up to each specific HPLC. Okay, so but the allowable change is between 80-20 to 60-40. So when you want to prepare the mobile phase, and this mobile phase, the methanol has to be HPLC grade. Okay, when you purchase the solvent, there are analytical grade and also HPLC grade. Analytical grade is like normal grade which you use as solvent for reaction, maybe use as solvent for to dissolve sample, for example. But when you want to use it inside the HPLC instrument, okay, you have to use HPLC grade. So when you want to buy this chemical from the supplier, you say that I want a methanol, but to use for HPLC. So they definitely know this is it must be HPLC grade. Even In fact, at the bottle of the chemical itself, the methanol, it will say HPLC grade, and the price is slightly higher than the normal analytical grade, because why it is much more expensive and you must use the HPLC grade. The purity is much higher, and the uh, solvent itself doesn't contain any like small particles, or which we don't want that to be introduced into the HPLC system, because the column size in the HPLC is very small, and all of the what to say, not the hose, the tube, okay, the tubing inside the system, okay, to bring out the mobile phase throughout the whole system, is also very small. So if let's say there is just one tiny particle inside, it can clog the tube, and there will be leakage, and that will have to be fixed. Okay, and you have to call the engineer from Shimadzu uh, to change the part, and it's not cheap. Okay, anything that relates to HPLC is not cheap. Okay, so you have to use HPLC grade solvent to prepare the mobile phase. Okay, once for the water itself, yes, you can use what do you call that, distilled water, but the distilled water prepared has to be from uh, I would say a very high level type of uh, purifier. Okay, we have that in our lab. For example, you can go and search one brand, Merck. Okay, MERCK, the normal brand, Merck Millipore. It looks like very like what do you call that? It's like what you have in your house. Those brand like Koei lah, Kuku lah. Okay, the size is about that, but it contain very tiny size of filtration. Okay, so that the water that comes out also doesn't contain any of this small particle. Okay, but you cannot just use tap water or any water that comes out from normal filtration. So once you mix this methanol and water together, or any other types of mobile phase, okay, that you want to prepare, either the polar or non-polar, it then has to be filtered. Okay, and the filtration has to be done using a very thin film, not like filter paper, but thin film membrane. Okay, this helps to remove any available particles that are still inside the solvent. Okay, so it's just like precautionary measures. So once you filtered, what we do next is to put the whole mobile phase. Okay, you prepare it normally in a bottle, what we call it as a shot bottle. So that bottle has to be put into the ultrasonic bath or the sonicator. So what it does, it will remove any trapped air bubble inside. Okay, another enemy of HPLC is also air bubble. Okay, so the air bubble must be removed altogether from the mobile phase. So once that is done, then only the mobile phase that you have prepared can be ready to be used in the HPLC system. Okay, so this is true even though the mobile phase that you use is just methanol. You are not going to mix it with any other thing. You still have to filter. You still have to sonicate. Okay, to remove any solid material or solid particle, and also to degas. Okay, to remove air bubble. Next is to prepare the sample solution. So sample solution containing the mixture of component to be separated. So actually the sample preparation depends on your what you call type of analyte that you want to test. Okay, if the sample is in tablet form, for example, if you're doing assay, the tablet has to be crushed first, and then to be extracted or to be diluted with any solvent, and then to be filtered, so that we just want to collect the liquid, okay, not any of the solid part, because uh, like earlier, the same reason as when you prepare the mobile phase. But for this case, for if you want to detect caffeine in beverages, all of the sample is already in liquid form. So what you have to do is to actually just filter them, okay, and they are ready to be injected into the HPLC, except for carbonated drink. Okay, so carbonated drink contain carbon dioxide, so it has to be degassed, to be all the carbon dioxide to be removed using the sonicator. Then only you filter. Okay, you filter using the filter membrane. Then the sample is ready to be injected. And then step number 3 is to switch on the instrument. This one later on we will watch on the video. Then you place the mobile phase into the solvent reservoir, turn on the pump, maintain the pressure, and then you can turn on the detector and wait for 5 minutes for stabilization. So over here, it looks quite simple. It's like switch on instrument, turn on pump, everything, and then just wait for 5 minutes for stabilization. But in reality, sometimes it will take more than 5 minutes. Okay, I would say the standard time for the HPLC system to be ready is maybe 30 minutes to 1 hour. Okay. And then number 8, and also step number 3 to number 7, actually it will be more suitable if you were in the lab to actually refer to the SOP, which is the standard operating procedure. Okay, but that's okay. This is like the general procedure. But from number 8, okay, procedure number 8, this is where you will set the lambda max, or the wavelength that you want to detect for the sample. And for caffeine, it is set at 275 nanometer. Okay, and then you run. That means run the mobile phase for at least 10 minutes. You allow the mobile phase that you have prepared earlier to be running through the whole system, through the tubing, through the column, and then it will be discarded. Okay, but that has to be done for about 10 minutes. This is to allow if there is any residual mobile phase from previous analysis. Okay, because you never know, the person who use it might use different solvent. Okay, so we want to make sure that all of that has been removed. Okay, and for this, even though it is stated to be 10 minutes, the time longer time that you leave the mobile phase to run through the whole system, the whole HPLC system, would be better. And then number 10 is correct the baseline for 10 minutes. So this actually means when you run the mobile phase through the system, okay, on the chromatogram, which you can see on the PC actually, they're supposed to form a flat line. You don't want it to form like your heartbeat, okay, up, down. We want everything to be in one flat line. So once that is achieved, then only the system is ready for sample to be injected. And then number 11, okay, you can inject the sample into the sample injector, and this will be run for about 10 minutes. Okay, so normally I will inject the sample and set the run time for 10 minutes, because actually for a sample that you have never done before, okay, it is good to have a longer run time. For example, like you said, just 30 minutes, because you never know where the peak for the chromatogram will come out. It could be at 3 minutes, okay, the chromatogram will come out maybe at 7 minutes, okay, but for this caffeine, normally it will appear less than 10 minutes. And then analyze the chromatogram for different components and you can prepare a report. So the identification of the eluted components can be carried out by comparing the retention time of the compound, of the component with that of standard. So the quantity of the component present can be carried out by various methods. So notice the word, the identification can be carried out by comparing with standard. Okay, so before you can actually inject your sample, okay, let's say you want to test caffeine in Pepsi drink, for example. So before you can inject the Pepsi drink, you actually have to run standard, which is pure caffeine. In our lab, we have pure caffeine. So that caffeine has to be dissolved, okay, and you have to turn it into a solution with known concentration. So let's say you want to prepare the concentration around 5 gram per liter, for example. So that the concentration has to be known. Okay, it doesn't matter what is the concentration, but you have to know the concentration of the standard solution that you prepare. So this standard solution will then be injected to the HPLC instrument first, and you will know at which runtime or at which minutes, okay, the peak will appear. Okay, for example, the peak will appear at 5 minutes. That is for the caffeine standard. So later on, when you inject the sample, okay, the sample, for example, the Pepsi drink, and if there is a peak that is coming out at exactly 5 minutes, you know that, this is the caffeine peak, or the peak that corresponds to caffeine. But if there is no peak that comes out at 5 minutes, then you know that the drinks or the beverage, your sample doesn't contain any caffeine. Why? Because you already have a standard. If you do not have a standard and you run, for example, coffee drink, Nescafe, and there are probably 4 peaks appearing in the chromatogram. So how are you going to identify which one will correspond to caffeine? So that's why it is important to have a standard in which that you can refer and compare. And with the help of the software in the PC, which is connected to the HPLC, you can further quantify, okay, by comparing with the area under the graph or the of the peak. Okay, for example, the standard, because the standard you already know the concentration, you can actually quantify or calculate what is the concentration for the caffeine that is in the sample. So this can actually be done. The quantity of the component can be done either by direct comparison. This is as what I have, as I said earlier, which is by comparing the peak area or the area under the curve of the standard and also the sample. The second method is to use a calibration curve. So that means you have to prepare the standard with 5 different concentration, and you have to inject this first and prepare a calibration curve. Then when you run the sample, you know what is the absorbance or the area under the peak, you can compare straight away. Okay, but actually using the first method would be, for me, it would be easier. Okay, now is the preparation of the standard stock solution. Okay, this one I didn't put above because above is more on the general method, and this is the specific method on the preparation of the standard. and also the sample. Okay. So for the standard, the final concentration that you have to prepare is 100 microgram per ml. So this is the final concentration of your caffeine standard. And also in terms of the sample preparation, uh, so if the sample is in solid, okay, you must dissolve into solution. For example, like this is coffee, you have to brew the coffee or make it into a drink first, and then what is it? Yeah, this one. If it's carbonated drink, okay, like Pepsi, Coke, okay, you must degas. You have to remove all of the gas from the samples. So that is all on the uh, procedure from the lab manual. Now we're going to look on the actual HPLC. So I want you to watch this video first, which is just on the basic of HPLC.
High-performance liquid chromatography is a technique in analytical chemistry used to separate, identify, and quantify each component in a mixture. As well as other forms of chromatography, in HPLC there is a mobile phase, which forced by a pump to pass through the system. And there is a stationary phase called a column, which located in an oven where the temperature can be controlled. The sample can be automatically injected into an HPLC system by the use of HPLC autosampler, or can be manually introduced into the injector using a syringe. There is also a detector attached to the HPLC system, which measures the analytes after its separation in the column. The pump forces the mobile phase through the column, and then the detector under high pressures. In the HPLC system, a vacuum pump and a degasser are connected to the pump and used to remove dissolved gases from the solvents. The pump drives each solvent to the mixing chamber, where mixing takes place under higher pressures. HPLC analysis commonly uses isocratic or gradient elution. In isocratic mode, the mobile phase composition remains constant throughout the procedure. Whereas in gradient mode, the mobile phase composition is changed during the separation process. Sample introduction can be accomplished in various ways. The simplest method is to use an injection valve. In the load position, the high-pressure eluting solvent flows to the column directly. The loop is loaded at the atmospheric pressure from a syringe via the needle port. Excess sample exits the loop via vent port. After loading the sample, the valve is switched to the inject position. The flow delivered by the pump flows through the loop, forcing the sample ahead of it, flowing to the column. Then, the valve returns to the load position, and the mobile phase moves the sample through the column. The separation is based on differential partitioning of the sample components between the mobile and stationary phases. The component which has more affinity to the mobile phase, consequently less affinity to the stationary phase, travels faster and eluted out first. And the component which has more affinity to the stationary phase, consequently more interaction, travels slower and eluted later. This separation can be carried out according to which type of HPLC used. There are two main types of HPLC, reverse phase and normal phase. Reversed phase has a non-polar stationary phase and moderately polar mobile phase. One common stationary phase is a silica which has been modified by attaching a straight-chain alkyl group to its surface, such as the octadecyl group, C18, or the octyl group, C8. In this case, the more hydrophobic the analytes are, the more retained they will be on the stationary phase. The more polar they are, the more they will prefer the mobile phase. In normal phase chromatography, the stationary phase is polar, and the mobile phase is nonpolar. This method separates analytes based on their affinity for a polar stationary surface, such as silica. In this case, the more polar the analytes are, the more retained they will be on the stationary phase. The more hydrophobic they are, the more they will prefer the mobile phase. As compounds dilute from the column, they interact with the detector. Different types of detectors can be used, such as the UV-vis detector, which showing an absorption spectrum in the ultraviolet or visible region. For UV detection, a deuterium discharge lamp as a light source is used. And for components detection in visible region, a tungsten lamp is used. In UV-vis detector we can also find entrance slit, lens, prism or diffraction grating, exit slit, flow cell, and detector for absorption measurements. Light from the lamp is shown onto the prism and dispersed according to wavelength. When the measurement is performed with a specific wavelength, the angle of the prism is adjusted so that the light of this wave can shine on the flow cell. As the compounds elute from the column, they enter the flow cell, where the bonding and non-bonding electrons of these compounds can absorb energy in the form of ultraviolet or visible light. The manner in which the final data is displayed is based on the computer and software. The number of peaks present can indicate how many components are in the mixture. Usually, the x-axis of the HPLC chromatogram shows the amount of time taken for the analytes to pass through the column and reach the detector. Typically, the y-axis, or the area of the peak, is a reflection of the amount of a specific analyte that's present.
Okay, so that is how a HPLC work. Okay, you have seen that video. I think is very good in terms of it shows how the mobile phase got mixed together, what is the function of the pump, okay, and then how the samples are being injected into the system and how it is being separated and also detected. Next is I want to show the type of HPLC that we have in
this
our
video
lab.
would like to show how to perform HPLC on the...
Okay, so this is I would say exactly the same, which is Shimadzu HPLC, okay, that we have in the lab. How to remove this? Okay, I think I have to.
Modular HPLC Shimadzu. First, switch on all the components. Then put the sample vials in the tray.
Okay, what she's showing right now is this has one extra, I would say, accessories or parts in which it has the auto sampler. So what does an auto sampler do is you just put the sample that you have prepared into a vial, okay, a very small vial, and then you can leave it in the instrument, and then the HPLC system will will do the injection by itself. So that means you can prepare like I think the maximum is 60 samples, okay, and it can do the injection by itself. So that means you don't have to be present while the injection is done. Unlike normal injection, that has to be done manually. Like the one in our lab, we have no manual injection. Okay? Like the one in the video also before this, that one is also manual injection. Okay, manual injection, you have to inject manually, and then every time you want to introduce a new sample, so you have to re-inject again and again.
Next, connect the solvent mobile phase.
So this is the mobile phase, okay?
Which has been detached and filter with the correct.
The mobile phase has to be placed into this type of bottle. We call it as a shot bottle.
while mobile phase B refer to 100% deionized water. Run lab solution program.
So that is the software, the same
Open
software,
PDS
the lab
system.
solution software. And this is the interface that you will see on the computer, okay, when the system is connected to the PC or to the software. And the yellow part is where you will see the chromatogram will comes out, okay. And this is also where you are going to set what is the flow rate for the mobile phase, the wavelength detector, okay, and also the temperature for the column. These all can be set, okay, and also whether the mobile phase runs in either isocratic or gradient, also you can set here.
Interface, key in the relevant setting. So such as the gradient, you have to key in how many percent of the pump, the mobile phase air, and how many percent of the mobile phase B, and this is an example. Pump mode, you can choose low pressure gradient, PDLM, wavelength, and also the column album, or you have to customize based on your experiment objective, and then you can set it as the method file, and then run auto purge, which is to make sure the system has been flushed properly using 70% methanol, and run for 5 to 8 minutes. After running, you can close the valves. And now you can install the column.
So that is what a column looks like, and this is the place where you place the column, and the temperature of the column can also be set. So if you put it like maybe 40 degrees Celsius, then the whole thing will be slightly warmer.
So in this video, this is an C18.
And the flow also, the flow, that means the orientation of the column that you put is normally the mobile phase will come from down, up, and then goes up. Okay, not from the top to bottom, normally from bottom to the top. And on the column itself, it will show the orientation of how to place the column, okay, an arrow.
Column, you connect the bottom part first.
So you cannot just simply attach.
Remember to follow the flow direction.
So that is the flow direction.
The arrow there.
So the small wire that you see, that is actually the tubing. Okay, it's very small. So that's why it is easily prone to clogging if you don't prepare your mobile phase or your sample properly.
Start the column flushing for 30 to 60 minutes. So by clicking on pump on and off icon in the toolbar, and make sure the column have no sign of the leaking. Fill the batch file, choose appropriate mobile method phase and the export location. Start the batch file, and everything is ready. Click batch run and go. Observe the pressure and the wavelength curves, and make sure everything has been stable and okay before you start up AutoLab and let it run overnight. After running, it's time to set the PDF file. First, choose the appropriate. Go to the data report at the left sidebar. Put the desired element into the lab report template, such as the chromatogram, peak table, and spectrum. If you have not enough page, you can go to toolbar to create the second page and put the rest of the element. Then you can
So
go
that
to
is how
preview
the raw
to see
data
whether
chromatogram
it
will looks out.
properly arranged or put in the correct ratio. And if everything is okay, you can click print, save as PDF. Choose your file destination and save the file. And a report has been generated. So before turn out the system, remember to flush the system with 70% methanol for 30 minutes. And
so once you have done your analysis, okay, before shutting down the HPLC, you have to flush. So we use the word flush. This flushing means you do not run any sample and don't use your mobile phase, but run the whole system with 70% methanol. So when you say 70% methanol, that means it is mixed with water. So 70% methanol with 30% water.
take out the column and start
So
properly,
this
and everything is okay.
is how
Thanks for
you
watching.
run the HPLC analysis using, especially using Shimadzu brand. Now I want to show this this video on how the caffeine analysis is done for Red Bull drink. Okay, must have the pure caffeine, which will be used as standard. And I think this time around, the mobile phase that the video use is using acetonitrile. So this is the filtration that I've said earlier, using the membrane film. Okay, it's not using normal filter paper, because you are actually just filtering the solution or the solvent. So this is the sample. It's using Red Bull, and if you go back a little bit, this one is putting it into the ultrasonic bar, sonicator, to remove any bubbles or anything. Okay, so the result you obtained found out that the caffeine is actually more than the stated amount on the can. This is the last video.
Hi, my name is Kylie Fawcett. I'm a student at Bridgeport Regional Aquaculture Science and Technology Education Center. I wanted to go into science and come to this school because science offers so many different techniques in coffee, tea, diet soda, and regular soda. So first and foremost, we're going to start with sample prep. In order to identify that there is indeed caffeine in the coffee, we need to run a pure sample of caffeine. To use this, we have a pure sample of caffeine right here. I took a small amount of this, put it in my motor and pestle, grinded it up so that it will dissolve faster. I took a very small amount of this and put it into about 3 milliliters of mobile phase, which is used in the instrument. Using a pipette, I mixed it up so that it will dissolve fully. That brings us to where I am right now. To ensure it's high quality enough to run through the instrument, we're going to filter it. We can use a 3 milliliter syringe and the filtering pads. First step first is to fill the syringe with the caffeine and mobile phase mixture. For the HPLC, you only need a small amount. So you really need to only get about 1 to 1.5 milliliters. Next, you attach the filter and start pushing it through into a new test tube. Once you filter it, it's important to cover it right away to keep that pureness and high quality you just gave it. So now we have our pure standard to compare the other samples against. Next, we're going to prepare the samples for the coffee. Here we have an old sample and a new sample. So to ensure that we'll be able to compare it, we have both. So what we're doing is making a 20% dilution. So I took 4 milliliters of the mobile phase, which we got from the instrument, and combined it with 1 milliliter of the coffee. We put this into here, shake it to combine it, and then transfer it to a test tube, which I have here. Next, we repeat the procedure of filtering it through the filter pad and covering it quickly. After that, I have my pure sample of caffeine and then my 2 samples of coffee. After preparing the samples, we can come over to the HPLC. The HPLC is actually a collection of many different devices. Up here, we have mobile phase. This is what's being pumped through the entire system and what will carry whatever we inject through the instrument. Next, we have the data system collector. This processes all the data. Down here, we have the pump, which is pumping the liquid through, and the injection port, where we put the sample into. Then we have the UV vis detector, which analyzes the solution, and the refractive index detector over here. So now we're going to inject our pure caffeine into the system. You take the test tube, and you can uncap it. There's a 100 microliter syringe you take. You can put this into the test tube, try to avoid having it touch the bottom, and you're going to push it out first to release all the air, and you're going to pull it in. You want to do this a few times just to wet the inside and to ensure that there's no bubbles captured in the syringe. Once you ensure there's no bubbles, you can fill it up to the 100 microliters. Make sure the injection port is on the load position, and you can inject it in. To ensure the injection port is full, you can inject it 2 to 3 times. Next, it's important to separate it and put it to side so you can clean it later. So next, we're going to run it through the system. In order to do this, you go over to the first box, you press auto 0, go to the second box and you hit auto 0. You switch the load position to the inject position, and you go over to the computer and hit auto 0 and auto 0. It's the 0 button in between the magnifying glasses. This scan is going to take anywhere between 2 to 5 minutes while we wait for the main peak to come out. During this time, you can take the syringe used to inject the pure caffeine into the sample and rinse it out with the mobile phase. After about 5 minutes, it's very important you switch this back to the load position so you're ready for the next sample. When each of the detectors has returned to the baseline and is no longer rising, you can go to acquisition and stop. This will stop the instrument and complete the scan. After the run of the caffeine, the experiment was continued with a run of the tea, diet soda, soda, and a pure caffeine. After each sample was analyzed, we printed the graphs, so now we can analyze to see if there is indeed caffeine in each sample. In the coffee, we found there was a peak at 3.13. In the tea, the peak occurred at 3.13 again. In the soda, the peak occurred at 3.13. And then finally, the diet soda had a peak of 3.130. So same as all of them. To identify this was indeed the caffeine, a pure sample of caffeine was run. The single peak occurred at 3.123. Although this is a little bit different than the ones we ran, we can successfully identify that it was caffeine in the other samples. So thank you for watching. This will conclude our experiment. Once again, this was determining caffeine in coffee, tea, diet soda, and regular soda using a Buck Scientific HPLC.
Okay, so you have seen the result that she showed earlier. Okay, so that is how you compare. Let me go back. So this is the pure caffeine, which is the standard that is supposed to be run first. In this test that she done, okay, the peak comes out at 3 minutes or 3.123, so about 3.1. So that is the retention time, and this retention time will be compared with the rest of the sample. So she has 4 samples, which is tea, coffee, diet soda, and also normal soda, which is the normal Coke. Okay, it's like Diet Coke and normal Coke. So to the sample itself, which is where is it? Let me try to look.
To identify this was indeed the caffeine, a pure sample of caffeine was run. The single peak, 1.3 again.
Okay, so tea, soda all obtained, she obtained a peak at 3.136. So what she did for this experiment is to actually just identify. What can be further done is to actually quantify, meaning determine what is the concentration just based on the area under the peak, or the peak area. Okay, the which this can be done actually using the software that is in the computer. So that is how you can analyze or determine a sample to contain caffeine or not. But the most important thing when you want to run or you want to analyze, okay, using analytical HPLC, is you must have standard. Okay, because without standard, how are you going to compare, or how are you going to determine which peak correspond to which analyte? Okay, for example, like in this case, she has 4 samples. If she might be lucky by having all of those peak appearing at the same retention time, okay, 3.1. So she can assume that it is caffeine. But let's say she just run 1 sample, which is just tea. So how are you going to determine whether that peak correspond to caffeine? So it is important to have a standard. Not just if you want to determine caffeine. If you were to do assay test for any other pharmaceutical formulation, like paracetamol, gabapentin, omeprazole, you must have a standard, and the standard has to be injected first so that you know at which retention time that it will appear. Okay, at which minute, 5 minutes, 7 minutes, the peaks will come out. Then when you run the sample, it should appear at the same retention time. Okay. And she's also using methanol water. Okay, same like what we have in the uh, lab manual. Okay, for this experiment, okay, if we were to be in the lab also, the lab report is just simply by I will run the sample, and we have the chromatogram. I will print out, and you can include it in your report. But for this experiment, okay, we are unable to have the chance to run those sample in the lab. So what I want you to do is to include a sample of caffeine standard chromatogram, just like what she shown over there, and also uh, chromatogram that contain a sample. Okay, meaning 2 different chromatogram. One is just the caffeine standard, and another one with a sample that contain caffeine. Okay, just have these 2 chromatogram to be included in your as a result for this experiment, since we can't be in the lab. Okay, so the sample can be from any beverages like tea, coffee drink, or uh, energy drink like Red Bull. Okay, but it must be under the beverage category. Okay, not like any other types of food or anything. Okay, so that is all on the second experiment, which is the determination of caffeine content using HPLC uh, instrument. Okay, so if you have any